Hi, I'm Kirsten Sakamoto, and I'm going to be talking to you about the applications of complex analysis in engineering. So there are many applications of complex numbers to engineering. Overall, any engineer will come across complex numbers in their field of work or in their schooling if they have to deal with oscillations in any capacity. So, for example, oscillations of the wind on a bridge or a skyscraper, um, shock absorbers designed for vehicles, those all deal with oscillations and deal with complex numbers in some way. So one of the applications to a specific field of engineering is in mechanical engineering, where complex numbers can be used in the calculations of rotations. Another is in civil engineering, which is my major, where complex geometry in the complex plane can be used to construct buildings, bridges, roadways, etc. And another application is in fluid mechanics, which I know I have personally taken for my civil engineering degree. I know that electrical and mechanical majors in the UMSL WashU program also have to take this course and gain a basic understanding of this. But in fluid mechanics, complex functions are used to describe potential flow in two directions. And the complex plane is also used for calculations of moments and forces on different structures, such as aircraft. And then another application related to engineering that is completely filled with complex numbers is that of quantum mechanics. So, quantum mechanics is a field of physics that deals with the movements and interactions of subatomic particles. Um, Physics overall is a foundation for all forms of engineering, but quantum mechanics is specifically used in electrical engineering and biomedical engineering, which deals with, biomedical engineering deals specifically with nuclear medicine that is completely based on the ideas of quantum mechanics. And using complex numbers in this field is necessary and it's so integral to it because it allows the use of wave equations and a much easier way to understand and solve without necessarily breaking any rules. And the fundamental basis of quantum mechanics is the Schrodinger equation that contains complex numbers. And this provides a mathematical prediction of particle momentum and position. So let's talk about that. So the Schrodinger equation has a few different components. So this is the kinetic energy. This is potential energy. And this here is the total energy. And we can obviously see here that this is an imaginary component of this. Another thing I want to point out is that the wave equation is embedded into this Schrodinger equation here. And it also contains complex numbers and requires complex analysis. So this here is basically just a complex probability distribution indicating the possible positions of the particle at certain times. So in 1927, Walter Heitler and Fritz London formulated the valence bond theory. And by using this formula and the wave function specifically, they proved that the two atoms in a hydrogen molecule are sharing electrons to form what we know now today as a covalent bond. So just kind of an interesting fact about where this equation got us. Um, so overall in quantum mechanics, the use of complex numbers is very interesting because they're used in more of a fundamental way. And what I mean when I say that is that the complex quantities that result from these equations, they're unable to be split into their real and imaginary parts and then used on their own. Um, So the complexity of using complex numbers in quantum mechanics is kind of puzzling, and it even puzzled and frustrated Schrödinger himself as he tried and ultimately failed to find physical interpretations for the real components of the complex quantities that resulted from his wave equation. So, yet another application in engineering is in electrical engineering specifically. Um, Specifically, Euler's formula is used a lot in AC circuits or alternating current circuits. So put simply, if two voltages with different phases are put into a circuit, they need to be combined into one before doing analysis. So whenever a sinusoidal voltage of some amplitude and phase is given, it can then be changed to exponential form with the amplitude in front and the angle multiplied by I. So the next step in this would be calculating the effects of adding a capacitor or inductor into the circuit, and the calculations for this is all complex analysis. So inductors and capacitors have impedance, which basically just tells us how the voltage and current will be shifted. And an inductor might have an impedance of 20I, which is equal to 20e to the I times 90 degrees. And that can be proven by Euler's formula. So let me kind of run through that really quickly. So say we have this using Euler's is 20 cosine 90 plus I sine 90. 20 times, this will be 0 plus I times 1, which reduces to 20I, which is what we were given in the first place. And then it's also important to note that the impedance I talked about previously, it actually causes a phase shift, which is the reason why complex numbers are needed for these calculations, as the complex numbers help serve as a representation of the phase. It just makes the calculations a lot less messy and a lot quicker to do. And then one other random piece of information regarding this is that these calculations will sometimes, and when I say these calculations, I mean electrical engineering circuit calculations, they'll sometimes use J instead of I as the imaginary number, which can be a little confusing at first if you're trying to look through calculations. But I also stands for current, so sometimes you may see J being used instead just to avoid confusion, but it kind of just depends on what book you're looking at, whose calculations you're looking at, which one they're using. Anyway, that is all that I have. Here are my resources. I would suggest looking into all of those. I found the YouTube video especially helpful. But yeah, thank you for watching.